Okay, it is the top of the hour and we're going to get started. Welcome to everyone. This is the MJSA webinar series, and every week we come to you with content that is important for us to know as a jewelry industry. During the COVID crisis, MJSA has made this series available for free for the entire industry. So if you're an MJSA member, it's always free to you. And we've been doing this series for 2 years now, and we plan to continue to do it and expand on it because it is a very popular event. So thank you, MJSA, for providing this because it is a true service to the industry. Today, we are going to be talking about additive manufacturing, and not just additive manufacturing the way a lot of jewelers think about it, which is in terms of growing waxes or polymers, but we're going to talk about going straight to powdered metal and then to finished metal products through additive manufacturing. So I have 3 wonderful guests to join us for this discussion. I'd like to introduce Arjun Aggarwal. He is in charge of sales for Desktop Metal in the United States, and they make the equipment that you can grow metal objects in. And we'll be talking more about that as we go. Then we have Veronica Nunez. Veronica is representing the designer part of this thought process. Veronica is coming to us from Zhongshan, China, so it's the middle of the night for her. She looks marvelously awake, considering. She is a bench jeweler, and she also designs for and grows jewelry in metal. So she knows the whole process, and it was very important to have that design perspective with us today. She is from Sao Paulo, Brazil. She has a studio in New York City since 2009, and right now she's working in China. And then we have Steve Adler. Steve Adler owns A3DM. If you're in the jewelry industry for any length of time, you probably know Steve. He has done everything from jewelry retail to being a design advisor to moving up the value chain to doing a tremendous amount of materials and manufacturing development in this 3D space. So that's just a brief introduction of each of them. After this webinar, there will be links that you can learn more about each of our guests. But for now, I want to kind of launch the discussion and get you guys talking about additive manufacturing for jewelers. And I guess my first question is, do you think that AM is going to become a bigger player in our lives with the tariffs that the US has experienced and some of the disruption with Chinese trade going back into 2019 and now the COVID crisis? Does this open a door for more additive manufacturing?
I'm happy to start off there. Hey everyone, thanks for joining the webinar here. Just again, my name is Arjun. I run product and business development at Desktop Metal. We manufacture metal 3D printers. So we design the technology or invent the technology, design the printers, manufacture and sell them out there. So this is a topic that's near and dear to our heart. As far as how the current situation is impacting the prevalence of additive, I think it certainly does. I think we're seeing the supply chain disruption that results when certain parts of the world shut down. In this case, it's due to pandemic, and other cases it may be due to geopolitical reasons or what have you. But there's plenty of issues, be it economic wars and whatnot. I think we look at supply chain reengineering as a long-term benefit to 3D printing. It's not something that a lot of people think about right away when they look at making an ROI case for technology. So I think that we've designed our machines and our technologies, and I think a lot of folks in the industry are designing to make sure that acute ROI is resolved and it's really compelling. You can find applications and use cases and deliver cost-effective goods. And that, I think, is really what we're seeing our customers buy our machines for. I think that situations like what we're undergoing now and when we come out on the other side, I think it'll continue to be a large thought kind of in the back of the head about re-engineering supply chains and whether it's offshoring or onshoring or co-locating with customers. I think it'll continue to be certainly a contributing factor, but from our perspective, we continue to view developing an initial applications and ROI as the primary vectors for getting folks to adopt additive. And if there's no case on that end, then it doesn't really make sense to re-engineer your supply chain. So first and foremost is the applications and the use case and the ROI. And second, and certainly more of a driving factor in today's world, is thinking about re-engineering supply chains.
So, Steve, you were in love with 3D growing all the way back in the 90s when people didn't really know what it was. And now I've watched you move, through the supply chain looking for ways to apply this passion of yours. So it's been a hard thing for jewelers to grab onto. Why is that? Is it just the expense? The skill set? Like, why?
So often it seems that product drives implementation, that in the early days of additive manufacturing, where we were making patterns for an already existing investment casting process, that there was a demand for other methods of creating patterns, for customization, for mass customization in some cases, but there was something driving the adaptation in those days for an existing process. When we moved into...
You mean like when you say something driving it, you mean like when U.S. companies started exporting their manufacturing to China and we needed to figure out how to make it faster, or do you mean something different?
No, I mean, with respect to the jewelry industry, at that time we had been doing some work in numerically controlled subtractive additive manufacturing, the making of dyes and grindings and so on, and subtractive. So we had the basis for computer-aided design even in the 60s at companies like Boston's. But in the 80s, as we started looking into the computer age, the ability to design things with programs and create 3D objects drove our desire to be able to output them, which obviously dovetailed into the use of additive manufacturing in the jewelry industry.
Let's define subtractive and additive real quick, okay? Because we think in these manufacturing terms, but I'm not sure that that's real clear to everybody.
Well, when we think about manufacturing from a computer design standpoint, we're talking about digital manufacturing. And there are a couple of ways of using that digital information. One is in the subtractive process and the other being in the additive process, or what we would call 3D printing. Early days for patterns for investment casting, and now moving into metals. So as we looked at the early days, what drove that adaptation was a desire from CAD to be able to create these 3D objects for casting. And in the beginning, it was for master patterns, for the ability to make the master and then make molds of those and then so on. And then, of course, as it became more cost efficient, we used it for production or serial production today. With metals, there isn't as much driving that adaptation. So I think, to some degree, we need to look at our metals and our applications for metals within the jewelry industry now. As far as the supply chain and COVID and that aspect of it, I'm very pleased to see applications driving implementation there. If you notice all the postings, the various social networks about how additive manufacturing is being used to make dividing systems for ventilators, and even the swabs that are used to go up your nose are being produced by 3D Systems and Envision Tech and other companies working with photopolymers. So there's something driving the application use there. I think after COVID, I don't see any real changes in that in our supply chain. I think we continue along the same path we have been.
Because you think people find casting sufficient? It's just not a big motivator?
I think that COVID to some degree has increased the hype in 3D printing, because we're seeing applications now for COVID that we're helping, and we're helping as a community, not just as one individual company. All of the end users of companies like Envision Tech and 3D Systems are also contributing. They're making face shields and so on. So it helps support the implementation of the process.
I see. That makes sense. But I wasn't sure about something you just said. So do you think that a additional awareness about what 3D printing can do can then create some demand in the jewelry industry for wanting to do more 3D, or are you not sure there's a connection?
That I think the 3D in the jewelry industry is quite mature.
For,
We're the
from,
only vertical market that has software that is dedicated to our industry. And not just one company that makes software, but multiple companies that make software. So we're rather mature. We're just moving on to the next step into direct metal fabrication. And it'll be adapted over time. But again, design has to drive that, and application needs to drive that.
so I want to come back to that in a minute, but I want to tip over to Veronica because you know what it's like to create work at the bench. What made you want to design direct from metal, and what changes did you have to make in your design thought process, if any, to go direct to metal?
So it was quite a challenge for me because there were definitely many aspects of the design that I had to modify in order for the metal printing. For example, gaps or that I needed to do in order for the printing not to be printed together. If I wanted moving parts, they needed to have some bigger gaps, or gravity. I worked closely with an engineer at this factory that I'm working with now. So I was all the time with her going through the designs and making sure that the walls were above a certain degree, like 45 degrees. So in order to print and not collapse when during the process. So I had to be all the time making little changes on my design. So that was the challenge part. But for me, the most attractive thing about the metal printing is to be able to really design some incredible detailed things that I would not be able to do by hand or by another technology, or very, very difficult to do by other technologies of metal, of jewelry making. And also saving, I think, a lot of steps, and maybe in the long term, in the long run, less waste in a way. So I didn't have to make molds. I could keep my files instead of keeping molds stock at home. So that attracted me, the additive manufacturing for my jewelry process.
So for our attendees in the audience, I'd love you to go to the chat box and let me know if you're already working with some form of additive manufacturing. Are you growing waxes? Have you done any metal growing? Or is this concept of growing metal from a powder foreign to you? Because if we need to give you some clarification about how it works, I want to do that, but I don't want to dive into it if you guys already know how it works for the most part. So, Veronica, did you decide you wanted to try growing from metal? How did you find out about it as a designer?
So I didn't know about this specific metal printing. I just contacted this company, and I sent my designs, and they gave me an advice. We could print this in this titanium alloy. Would you like to try that, to try this project with us? And then I decided to work closely with them, and was really a wonderful experience for me because it allowed me to really understand a little bit more about this world. Now, being a jewelry designer, sometimes you're not an engineer, so to work closely with an engineer and understand how the process works for metal 3D printing is very different, than, for example, wax printing, or just jewelry making basic techniques like carving or metal smithing, just, on your own. It works very differently.
Very differently. Arjun, could you give just a brief description of what happens in a machine when you're building a piece of metal from powder?
Yeah, there's a couple of different processes for metal 3D printing, and I'm not sure the one that Veronica uses. I suspect it's a laser powder bed fusion based process where you're welding with a laser. But generally speaking, the way it works is you have effectively a box, and you spread layers of powder. and every layer of powder, you're fusing to prior layers, or you're creating the part on that layer by either taking a laser and applying a heat source and effectively sintering or welding the metal particles together, or you can use technology called binder jetting, where it's very similar to 2D inkjet printing, where you basically jet droplets of a liquid agent that holds the powders together, and then you separately thermally process them to form a dense solid. So it's there's a couple different processes. Each come with its own design limitations. Can the other speakers go on mute really quick?
Yeah, sorry, that was a birds flying by.
Thanks. Yeah, I'm getting a little bit of feedback from everyone. So, you know, every process has its limitations. Traditional manufacturing has its process limitations. Lost wax mold has its process limitations. I think it's no different with metal 3D printing, and even within metal 3D printing, you know, the different technologies have their own separate limitations. That said, I think that when you are directly printing in metal, you have the opportunity for a much wider set of geometries and geometric flexibility than you do with a traditional manufacturing process. And I think that's why there is interest in directly printing with metal. I think, as Veronica mentioned, you're also just eliminating steps. So rather than having to deal with tooling and molds or 3D printing a lost wax mold and then using that lost wax mold to cast a part, you can just print the part itself. Part of the challenge has just been it hasn't really been economic. The whole reason our company exists is because traditional, or I guess what I would say incumbent metal 3D printing technologies are either too slow and too expensive, or on the other end of the spectrum, they're not really safe. So it's been hard to use direct metal 3D printing in the jewelry industry. I think there are a lot of innovations that are coming out now that are solving that. So we have printers, for example, that can print, extremely fast. I would say hundreds of thousands, millions of pieces, maybe when it comes even to jewelry per year. So the throughput is really getting up there, and as a result, the costs are coming down. And the quality that you're getting can be pretty good. You know, I don't think that you're going to get parts that you can just necessarily for the jewelry industry put into a show store, but
not. Hey, I'm going to jump in here for just 1 second because I'm
Yeah.
going to break it down a little bit for our jewelry bench jewelers who may not have experienced this. So, you know, when you're forming a piece of metal, you are, you're sawing, you're bending, you're doing all kinds of mechanical activity to it, or you're creating a mold and you're pouring in molten metal, and then you're doing the casting process. In growing, there is a bed, and the powder is getting laid into the bed, and it's being built up layer by layer according to the design. So it's literally being formed from the ground up most of the time. Is anyone doing it from any other direction? I think it's always from the ground up. But so the piece that you're making has to be envisioned by the computer from the ground up. And so there's going to be a little bit of, if it's a ring, a little bit of there. And then as it grows up, it's going to come up around that circle, and then it's going to come up to the top. So when Veronica was talking about needing to leave spaces, there has to be something in the design that fills in that hole so it doesn't turn into a solid lump of circular metal. So picture your piece of jewelry growing in it's very tiny particle pieces of metal from the ground up. And that's a very different design vision. I want to get Steve and Veronica to talk for a moment because you've both experienced the challenges of translating traditional jewelry design thought process into an AM design process. And then I want to get some of these questions because surface roughness, surface finish, density, they're all really important questions that we all have about AM. But let's talk about translating design. And then, Arjun, we're going to get back to some of those things you were heading toward, which I think we need to get to as well. So, Steve, and you can be muted. There you go.
So from a design perspective, we've always had this this issue of how can we design in 3D and still have it suitable for the casting process. Certain metals can only withstand certain thicknesses. For instance, in the case of gold and silver, of course, we can cast a much thinner section than we might be able to cast in platinum or palladium. The higher temperature metals are much more difficult to cast because their liquid to solid temperatures are so close. They freeze off very quickly and makes it very difficult to be able to cast intricate designs where they go from thick sections to thin sections and then back to thick again. So in cases like that, we're looking at design differently for metals, particularly in the higher melting temperature metals. For the future, I see more adaptation in what we would call alternative metals for jewelry rather than the traditional gold and silver. For the most part, most anything that we design, we can cast in gold and silver. But when we move into the exotic materials, the titanium, the cobalt chrome, the tungsten carbide, some things I'm working with like niobium alloys and tantalum alloys, these are materials that can be oxidized in a variety of colors, similar to titanium, and probably offer the best opportunities moving forward for the jewelry industry because they are difficult to cast, right, and because they can be 3D printed. So from a design perspective, I think we start looking at other materials and looking at alternative markets, particularly as we see gold now approaching the $2,000 to $3,000 range within the next couple of years. This will become more difficult and will focus us more in the alternative metals.
I love that perspective. A lot of people are thinking metal printing may not be as interesting because I can't get to a great gold or platinum powder. But what you're saying is don't think about it that way. Think about the design opportunity in all the other metals that otherwise we couldn't work in. That I like that.
Well, even in platinum, Andrea, I mean, there are so many designs that people want to create in platinum now because it is inexpensive in comparison to gold. Yep. But now you can buy a platinum ring for less money than you can buy an 18-karat gold ring. So now we look at the opportunities in design for 3D printing of platinum, which were not available before. We have an incentive now to be able to make lightweight 3D printed platinum jewelry that we cannot cast.
Veronica, your work is extremely architectural. Was it that architectural when you went to 3D printing, or did you become more architectural in your look as you could get those? I mean, casting doesn't like to go around corners, but metal growing doesn't mind. What was the influence?
I've always loved architecture. And also, of course, since the beginning, since I started carving and even working, on my bench, I already took inspiration from architecture. But for sure, the 3D printing allowed me a much wider ranges of intricate designs and things that I could not make so easily. For example, moving parts within parts. That was almost impossible to do by hand. Very intricate designs, very, very specifically thin walls and things like that are very difficult to cast or almost impossible to cast. It can be done by metal printing, which is really interesting. And like Steve was saying, the new materials are actually a whole new world for us jewelers. I found it very interesting working with the titanium alloy just because it is very lightweight and it is excellent. The corrosion resistance is fantastic. So there are a lot of benefits using these alternative materials as well. Yeah.
Now we are getting,
and of course the price which will be very
for recovering economies. I think price is really going to be a big focus, certainly for the next few years. There are, no surprise, our bench jewelers are asking one of the big questions that's popped up a few times now. Are the pieces that are grown in an AM machine as strong when they are done as if you had cast them or hand worked them? Or do you need to do something like hip them or do something to increase the tensile strength?
There's no need for that. I think a lot of the materials that or the parts that you get out of metal 3D printers, I mean, we qualify our metal 3D printers to meet MIM industry standards. So you have really strong parts. They act very similar to castings, to be honest. Densities in the mid to even high 90s, at least for our technology. But broadly speaking, you should be able to achieve mid 90s densities, whether it's laser powder bed fusion technology or a binder jet technology. So I think the material properties are going to be, from a strength perspective, they should be totally sufficient. I think the real question is going to be more, especially for the jewelry industry, around the look of it.
Well, here in a second, I saw a tiny eye roll from Steve. Did you disagree with that, Steve?
Well, I'm sorry. I apologize.
No, don't. If we can't
No, I think
room, I love to read this.
I've had some practical experience here, so that's why I kind of rolled my eyes. With respect to laser powder bed fusion and, of course, the binder jetting technologies, yes, we can get in the high 97 to 99%, but what we generally see is microporosity. Not significant voids within the article that would give it some structural disabilities, but so small that they are in the micron and submicron range. So much like bench jewelers when they are working with castings and platinum, that they have to burnish the surface in order to get good hard metal in order to polish. The same would be true of products made from additive manufacturing, no matter what technology you're using. Hot isostatic pressing would be a benefit in most of these metals because as we go to polish them, we get the drag out of that microporosity. The compounds that we use, rouge and tripoli and such, as they hit these very small bits of porosity, they drag that compound like comets across the surface. So in order to get a truly high polished surface, you have to burnish that metal first in order to get a nice bright.
Yeah, and that's what I was getting to. I think I was speaking to at the macro level, the strength of the part. It should be it's equivalent to a casted part. But when you get to look and feel for the jewelry industry, yes, I agree. I mean, you can get densities in the mid to high 90s. I think we would look to you guys to understand a little bit better, okay, what does that mean in terms of fit, finish for the jewelry industry? Does it require hip? Does it require, polishing? The good news is that all the parts are fully compatible with those techniques for post-processing.
Absolutely, and commonly used. It also depends greatly on the alloy and the type of material we're working with. For instance, the common alloy used in platinum for the jewelry industry is one of 95% platinum and 5% ruthenium. And that particular alloy has a tendency for microporosity and solidification anyway. Right. As it solidifies, it tends to shrink on itself and creates porosity. So even if you have the fullest, densest part, some of this has more to do with the metal in which you are printing with than it does about the process that you're using.
So has that been consistent with your experience, Veronica? Are you, what are your finishing processes after you grow them, and understanding that you're working mostly in titanium, right?
Yes, I didn't finish the parts myself. The factory took care of it, but I agree that it probably, the 3D printing the deposits, right, would have some sort of micro porosities, but it's not visible, at least for me, the finished parts. It actually looks very good, the finished product. Looks quite as, for me, I don't see a visual difference from the casting, from, piece to the printing one. It's not visually for me. Clearly as you can see, but I'm sure if you put a microscope, you probably can see that, microporosities. there on the.
Yes, and again, that is we would expect that from titanium. Titanium and cobalt chrome, we would not expect the degree of microporosity being there. They're much harder metals to work with, so they can be polished more readily because they are harder.
So,
Yes.
Steve, this is occurring to me as we're talking about this, that for jewelers who are used to dealing with silver, gold, platinum group metals, they kind of understand the way those metals behave, even if they can't speak about the, material properties like you or Joe Strauss or Stuart Grice can. They get how these metals behave. So,
How they feel, sure.
but so growing in different metals also means people have to get a new feel for a bunch of different metals, doesn't it? Or does it?
It's a whole new world.
Okay.
I think, you'll see some similarities. For instance, the use of tantalum and niobium alloys will probably become fashionable because these alloys have some density. Tantalum has a density similar to silver. It has the feel of a precious metal. And because it can be oxidized and made in a variety of colors and it is hypoallergenic, we'll start to see the use of 3D printed tantalum and the 3D printed of niobium in some of these, what I would call fashion jewelry applications. I don't know that we'll see them immediately in bridal jewelry, but you'll see them in other applications.
So Arjun,
And ceramics and composites as well.
In dealing with your customers, how broad is the range of metals that your machines are prepared to handle?
It's pretty broad. I mean, there's it depends on the technology, first of all. So not all metal 3D printing technologies created equal. Things that use laser powder bed fusion technology, where you're building it layer by layer with a laser, has restrictions that binder jetting, where you're using ink to hold the parts together, does not. So I think there is broad applicability. It's a matter of process development and getting it to the right spec for the end market. So, in jewelry, density is going to be one of the biggest things, and making sure that you can get parts that meet that density spec. So, I think, yes, we certainly look for, obviously, there's a benefit to making parts with materials that can't be casted. But on the other end of the spectrum, if those are niche materials, as a manufacturer and as someone who looks at how to do process development, we're more inclined to do something that is more mainstream. So we started looking at things like gold, silver, bronze, and some of these other materials, trying to figure out how to make it feasible. Because if there's a way that you can do it more economically than with casting, which some of our printers can do because of the speed and the throughput, then we think that the geometric flexibility combined with that economic advantage can provide sufficient reason, if we can get the quality of the parts coming out, to start using metal 3D printing.
So let's talk about that. Is my microphone on or off? Can you guys hear me?
Yeah.
Great. Okay. Let's talk about that for just a minute, because when we're casting, we have lots of metal waste. Okay. We have a tree, we have a button, we just have all of this metal waste. Do we have less metal waste with additive manufacturing? And does that offset some of the costs of getting into that technology?
Certainly there are types which have less waste. Binder jet printing certainly has less waste, and Desktop Metal has a very innovative method for their studio system, which uses less waste. The traditional powder bed fusion that most people understand with a laser does have some significant waste factors, and that won't be changing too much. It's just the fact of gravity. But binder jetting, as it becomes more popular and more cost effective, is certainly a less wasteful method. All of the powder that is not bound together by the binder is certainly reusable. So no, not a lot of waste there at all.
On our binder jetting systems, we see powder recyclability upwards of 99% or higher in many circumstances. If it can be recovered, it can be recycled. So I think where the delta comes in is in the recovery, where it is a loose powder process. So there is the chance that depending on the piece of equipment that you're getting, it could have really good sealing, it could not have good sealing. But generally in binder jetting, if you can recover it, you can recycle it. Laser powder bed fusion it's similar, but to a lesser degree, because the powder, the quality of the powder degrades over time. So you can't get all of the reuse that you would get out of a binder jetting process.
So is that like I'm picturing my goldsmiths in the audience, picturing all this fluffy gold floating away and not being recyclable. Is this something we have to worry about?
Again, depending on the technology.
Yeah, depending on the technology and depending on the equipment. There are certainly some pieces of equipment that are more robust in terms of being able to capture the powder than others. Yeah.
Fair enough. I'm still seeing a lot of questions about porosity. What about surface porosity? How is a finished, and I realize we have to go metal to metal. So maybe we could talk, I think there's a lot more experience growing silver than gold at this point, but I might be wrong. Like metal to metal, what's the surface porosity comparison to casting?
So the surface finish is a function of the particulate size that we are either melting or binding together and then sintering.
Okay, so the difference between casting grains and their or powder and their shape?
Think about it this way, that there's always this little bit of powder that is adherent, that was not necessarily part of the part that you wanted, but is adherent to the outside of it.
Okay.
And sometimes it's only attached by, small molecules holding it in place. And in other cases, it's sintered to the surface. So we generally find that, for instance, with powder bed fusion systems, that there's about 0.2 of a millimeter before we get to what we would consider polishable surface.
Okay.
So that can
You're speaking to surface roughness more than surface porosity. Okay.
Yes, and that's really, those two terms are negligible. Porosity would mean that it was totally encapsulated. Surface roughness would be the craters and undulations on the surface.
Yeah.
So generally, we go back to our basic jewelry principles here, which are that once we get a piece of raw material, whether it be cast or 3D printed, that the burnishing process takes place either by bead blasting or by mechanical means to densify that outside surface. And generally that layer is somewhere between 100 microns and 200 microns, 1 to 0.2 of a millimeter thick. With binder jet printing, because the particulate size, the size of the powder is so much smaller, that surface is actually much better after sintering than you would get out of a powder bed fusion system. So it really does depend on the technology that you're using. The high volume systems in binder jet will certainly produce a part that will be denser overall and will have a better surface quality. The fact that it doesn't require any support systems to hold it while it's being built means that you don't have a lot of waste, and will probably be in the final analysis, the technology that we will move to, because it will provide us with the best surface quality.
So Suresh wants to know, in practical terms, does that mean you're down to a cloth polish at that point, or are you still grinding?
The 0.2 is certainly a grind, an emery. And then beyond that, probably a compound, or if you're doing mass finishing, several steps of mass finishing from there.
So should we expect a faster finishing process from finished grown part to the end than we do with casting?
Certainly with binder jetting. With powder-based systems and others where you have a support structure to remove, no, there's work to be done, yes.
So then does that extend your jewelry processing time, or is it about the same as casting at that point?
About the same.
Same?
Yeah.
All right.
I think there was a study done by Damiano Zito from ProGold on the timelines for casting versus additive manufacturing. And I think that's available on the Santa Fe Symposium site.
Yeah. It is actually. I've looked at that recently. Susan, yes, the medical device industry is extensively using this technique. They're one of the big takers of this, hoping to improve their manufacturing process. So, is loss of powder material? So, I asked that question about fluffy gold, and then maybe I created more anxiety than I needed to. So, how much material loss do we experience with this?
In powder bed fusion systems, we're seeing somewhere between 3 and 5%. When most of these systems, for instance, the EOS systems or the Concept Laser or Trump or SISMA, any of these smaller systems, we're seeing anywhere from 3 to 5 if you're careful. If you're not careful, well, you can lose a lot of powder, sure.
Well, that's true. Casting shop too. Another question is, Nans is asking, if I grow a resin and then cast it, is that going to have a significantly different surface than if I just print it directly in metal?
Yes. The casting process is much more refined than the additive manufacturing process. If you have a very cold mold that you're throwing metal into, you will get a pristine surface from your pattern, because the patterns we use today for 3D printing are much higher resolution than we're able to achieve by powder. And I'm sure, the common B9 Creator and EnvisionTech and all of these photopolymer-based systems make an exceptionally smooth surface. So we would expect to get an exceptionally smooth casting.
Okay. Veronica, what metals have you experimented with so far? Has it been all titanium, or have you played with other metals?
The only metal experience printing was titanium for me, and titanium alloy. That was the only metal that I experienced so far. But probably in the future, I will try different materials.
I'm seeing another question about, is it, it's like the cast in place question. Can we grow a piece of jewelry around a gemstone?
Not easily.
Not really possible today. I think the metal parts have to be created on themselves, and then any stones or any other components of the jewelry you'll need to integrate into a piece thereafter. I think it'll be a while before you can start talking about printing around things and over things.
There has been some encapsulation of items within items, a box within a box, sort of thing, pearls within a cage, to be able to isolate things that will rattle around. But the ability to place prongs or to place a bezel is not going to be possible.
Because
you'll have the stone in the way of the recoder as it goes to apply the next layer.
Yeah, those are the environments in which you're printing. You can't just put something in the powder bed and disrupt it mid-print. It's start to finish. It's a contained thing. You can't really put things into that powder bed during a print.
Hopefully in the future.
Maybe. We'll see.
So if a jeweler's listening to this conversation and they're thinking, that sounds really cool, I'd like to try that, how do they get started? And what are the risks?
Well, every technology goes through a phase of bureau services and then adaptation by the end user. So we are at the stage now where we are at bureau services. The average bench jeweler would not go out and spend the $200,000 plus to be able to buy a 3D printer, because the applications don't support it from an ROI perspective. But there are a large number of companies that are doing work in the aerospace and medical fields that are printing, as I said, what we would call alternative metals, that would be perfectly happy to take an STL file and print it in stainless steel or in titanium 6-4, which is commonly used, or cobalt chrome, and work from those metals. And as time goes on, they will offer a broader range of metals. In Europe, there are a number of bureau services running precious metals, not so much here in the United States. Hasn't really found a market here as yet, but there are places that you can send files to and have them printed and then have them sent to you. And that's probably the stage at which we're at now. Desktop Metal is moving towards marketing a somewhat less expensive system that may be applicable in some cases for jewelers. And I've seen systems that are now approaching the 75,000 euro to 100,000 euro powder bed fusion systems. So those prices have now come down from what was 5 years ago 400,000 down to under 100,000. And jewelers will start to look at those here as they get into the $75,000 to $50,000 range. We have some people that will risk that kind of money to be able to experiment.
Do you guys have the ROIs on, say somebody was going to buy a $100,000 machine? Do you have a sense of the ROI in terms of how much jewelry you have to produce to make that pay off? Granted, we could be talking the difference between fine prices and fashion prices, but is there a...
Arjun, I'll leave that to you. That's
I mean, it totally depends on the technology, and I'm trying to speak more broadly without saying too much about desktop metal here, but it does totally depend on the technology because, between laser-based 3D printing and binder jet, there's a huge difference in throughput. And that really comes down to the fact that with a laser-based 3D printing system, you are tracing out your shapes. So if you have 10 rings in a layer, you have to trace out every single ring. Versus if you have a binder jet based process, you wipe across an entire layer at once. So the throughput is extremely different depending on the type of technology you have. Our systems, or at least the ones we think are applicable for the jewelry industry, use binder jet technology. So the number of, or the quantity of pieces that you can make will be a lot higher, may be able to attain a faster ROI than with a laser powder bed system. But ultimately, that doesn't matter if the quality of the parts isn't sufficient. So you have to make sure that you're choosing a technology where the quality gets you what you want. And then once you're there, it's like, okay, now let me consider the ROI. But I would echo Steve's statement. There's a lot of service bureaus. I think one great way to get started here, particularly to understand if the look and finish of the parts works for you, is to try with something other than a precious metal. Get started, looking and experimenting around with stainless steels and see if the in polishing that you can, it's not going to be exactly the same, but you can get a decent sense for what the surface finish is going to look like coming out of a machine. It's going to be pretty comparable from material to material for 3D printing. So it's worthwhile at least evaluating from a service bureau perspective. Maybe they don't have precious metals, but if you're interested in getting started, you could take a look at a lower cost base material and see if the fit and the finish work for you.
So,
Arjun,
quick question. I just want to ask Veronica real quick. When you're doing your designs, how many pieces of each individual design are you running at a time? Like what kind of volumes are you doing per style?
Right now, I do low volume, and that's casting or also 3D printing. And what is very interesting about the 3D printing for me is the 3D files can be easily edited. So if I need to change, for example, if I'm not satisfied with the thickness of or the size of the holes, or if I wanted to make changes of the dimension of the ring, I can easily make it on the 3D file. So I think that's also what I like about the 3D designing, in the computer. You can just change the file and send to the factory, and they can, make a few pieces at a time. It doesn't need to be a high volume. So for this project, for example, I printed about 30 pieces, for the titanium. So I use that, just to see how it turns out, if I like it or not. So you can easily do a small quantity too, you know.
Okay, that's interesting. So it doesn't have to be high volume. Steve, what were you trying to say?
I was going to say, for an ROI, so often the biggest concern is, well, how much metal do I have to put into this machine? Because indeed, if you're going to have, let's say, a 3% loss in your process, and you have to put in $1 million worth of metal to make one piece, then it becomes a real factor. Some of the smaller laboratory sized equipment, one that I recently used had an envelope that was only about 32 millimeters in diameter. And in a case like that, you're not so much worrying about having large volumes of material. But in that particular case, I think we used somewhere around 1 kilo of gold just to make the one piece. So you can't look at it as a cost of ROI for the material. You have to consider that a cost of doing business, much like if you were electroplating. Yep. You wouldn't think about how much gold I have to put into a large electroplating tank in order to plate a dozen pieces at a time. That gold stays in there. It doesn't go away. It's part of your cost of operation. So it's not an ROI issue.
But more of an investment up front.
Right.
It's more of a base capital. How much, I guess, sustaining capital do you need? Yeah, right. I think one of the good things about at least binder jetting is if you only want to print, a layer of rings or pendants or what have you, pieces of jewelry, you don't need to fill up the whole build volume. You have to go to the layer height that is sufficient for your amount that you need printed. So there are ways to mitigate. But yes, the amount that you use is going to be mostly dependent then on the XY dimensions of the build plate.
Right. And generally with jewelry, we see that height as being under 50 millimeters. So in general, that's what we see as an average height if supported vertically. And obviously with other technologies, you may not need to do that, but that's kind of what we see is the frightening part about, well, how much gold will it take to fill that machine up to 50 millimeters? And can I make enough pieces to offset that?
Yeah. Two quick questions coming out of that. Steve, you referred to the envelope. For the people who are not used to working with this technology, what do you mean by the envelope?
Height, width, and depth.
Okay. So
how tall, how wide, and how lengthy.
All right. Cool.
The area in which you're going to put that powder in.
And then the second question, and this has been asked by our attendees, is what about material reuse? What are the rules around remelt and reuse of powder?
Depends on the alloy. With platinum, over and over and over and over again. With gold, yes, you're going to experience some loss of the lower melting temperature constituents over time, and you'll get a pickup of oxygen from time to time as well. Most companies are taking these, what we would call revert materials, and sieving them to remove the larger particle sizes that may have agglomerated in the process. And then they take the remaining powder and dry it to make sure that it doesn't have any moisture to it, so it will flow properly in the next round.
You don't like
there's
powder.
Yeah. But in a lot of cases now, this equipment, all of this takes place within the machine itself. Mm-hmm. These machines have become far more sophisticated about the handling of powder, and in a lot of cases, you don't touch it. It stays within the machine, it gets sieved within the machine, and it gets dried in the machine and put back into use.
Okay. For the gold reuse, because I think this was very specific to this person's question, do we need to see the same kind of add fresh percentages that we get in casting? No? Okay.
No, it's not like casting where you have to put a third more back in or a quarter more back in of revert gold. No, it's reusable. It's never melted, so it never changes.
So we're running out of time, but there's one more thing I wanted you guys to talk about, which is if a designer's used to, and I want to get to the rest of these questions. If a designer is accustomed to designing in CAD, they grow their polymers or waxes and they cast. Will those same CAD designs work to go straight to printing metal, or do you have to do something different?
Good question. The metal process is more accurate than the casting process. For instance, if you were making a platinum ring and you made a pattern and then investment casted, you'd have to compensate for the shrinkage of that metal when you're casting. When you're printing it, what you print is what you get. It does not change. There is no shrink.
That's not true.
Well, with the exception of binder jetting, that's a whole nother.
Well, how much shrink in binder jetting?
There's can be up to 15 to 20% shrinkage, but many of the companies that deploy binder jetting solutions automatically compensate for the shrinkage. And it's, in our systems, we calculate the shrinkage based on the geometry and the material, and we apply an automatic compensation factor. So it's not something that the designers or the operators ever have to worry about.
It's a different kind of shrinkage than typically you would think of from casting. Casting, we think of shrinkage as you're feeding the piece and it's cooling. The shrinkage that you get in the binder jetting process is isometric. So it shrinks uniformly across the entire piece. And that is the primary difference, is that it is a predictable shrinkage.
So that's why you can do an adjustment to the design and not have the designer kill you, because it's math.
That's right. That's right. It's something that we do every day for all the parts, that engineers put into our printers. It's automatically compensated. And as Steve mentioned, it is relatively isotropic, so you're going to get it about the same in every direction. And it's calculable based on the material and the parts.
So Veronica, you said when you first started working at AM that you worked with an engineer regularly to get your designs ready. What were you working on?
We were working on the details. For example, if the parts were interlocking and they needed to be movable, they had to have a bigger gap in order to be able to move around. And also the angles, that was the really hard part for me, because I designed some really different things on the 3D that I wanted to have print my ideas. But then the engineer kept saying, no, you have to change the angle. It has to be, 45 degrees so in order not to collapse when it prints. So there's definitely some tricky parts, at least in my experience.
I would say that I 100% agree. I think that what you'll experience is that not all casting designs or designs for casting are going to be suitable for additive. So you could do it, but it may require supports, which would then increase the amount of time it takes to finish the part. So there's things that you can do with additive that are just not possible with casting, which is one of the amazing things about the technology. But if you're taking a casting design, you may need to modify it in order to get that fit and finish you're looking for.
So it kind of takes us back to what Steve was saying at the beginning, which is don't just think about it as an alternative to casting what you're used to casting, but think about it in terms of the design opportunities that exist that you can't get to now. Now we're getting a lot of questions about, okay, so who are the service agencies that I can go to do this? I mean, should we compile a list afterward and send it to our attendees, or do you guys want to rattle off some ideas of places they can go?
Certainly you can contact me offline depending upon the kind of material that you're looking for, and I'll be happy to give you some ideas of companies that have that particular technology. Does Desktop Metal provide any bureau service?
We do not, but if you search, locally, just Google 3D Printing Bureau and Desktop Metal, I think that's probably going to be one of the best ways to find it. By and large, service bureaus are very localized. There aren't like a lot of really big 3D printing service bureaus. They tend to be smaller in scale. And so it might just be a matter of having to do a little bit of Google hunting.
So, and certainly the links to all of our experts today are available. When we close out of this session, you go to a page that will give you links so you can get a hold of them. And looking through our questions, Nance Allen wants to know if there are new alloys being developed for printing fine pieces in platinum?
Not so much alloys as powders that have a particular particle size distribution. The object in working with powders is how do we make them fit together tightly? And traditionally, powders have been from a size, hypothetically, from 15 microns to 45 microns. And somewhere in the middle there is the optimal size. But now we look at the mixtures of these powders, and we're starting to see better ways of mixing them so that they mesh together better
Compensate.
and are tight. And that's what you'll start to see is the perfection of materials in current alloys that will operate better in these machines. New alloys might be possible in the jewelry industry with the FTC guidelines changed now. Those opportunities exist. Theoretically, you could have your 5 carat and your 23.2 carat. As long as you stamp it that way, you can have anything you like. But I don't know that anything is driving that per se.
We have a question about gold filled, so multi-metal gold filled. Are any of those things possible?
There's some experimentation in bimetal and trimetal. We're concerned about the point where they meet and how reliable those bonds are.
I would say reliable, high quality multi-metal printing is at least a couple years out. Yeah,
it's a ways off. I wouldn't look for that to happen. I have seen it done, and there are some companies that are doing what I would call a Rube Goldberg method of doing it, taking the gold out and then putting another gold in and then putting the machine back together again. And yes, there's a way of doing it, but not a productive way.
I'm also seeing a question about when buying a machine. There's one question, what's the technician availability for service and support? But then that stimulates another question in my mind, which is, what about at the pace that the technology is changing, how likely are you to buy a machine today that's completely out of date 2 years from now?
I'll give you a very good example of that. I did some research for Trump. That's with an F on the end.
I hear you really pushing that every time you say
it. They're a large laser manufacturer in Germany, and the machine that they put in my facility for that research, by the time it arrived, it had been already superseded by the next model. So yes, that's just the nature of technology. It's going to change every year, every 6 months. It's always incremental, and there's not much we can do about that. I just bought a new iPhone 11 because of that very same reason. You have to buy the next toy.
I will say, I think in the coming years, you'll start to see more hardware as a service business models that allow you to still try that new equipment without the burden of a large upfront capital expense. And without having to risk that obsolescence. They're not super prevalent today. I think the industry is just starting to experiment. We ourselves are just starting to experiment, but in a couple of years, we could see that that business model start to become a lot more prevalent.
What about maintenance and support? Are these machines that somebody can actually train and learn to do, or are you always pulling in a technician if you need help with the machine?
Depends on the process. I think most vendors of the equipment have service, robust service offerings so that if something goes wrong, the onus is not on the customer to learn how to repair it or fix it.
No sé si I should hang up and call again. I should just go.
We hear you.
Were you saying something, Veronica? Okay.
I think she's lost us, but we haven't lost her.
Oh, okay.
So from a practical standpoint, I'm sorry, I've forgotten the last question you had.
Well, I was wondering about whether the equipment would become obsolete quickly, and also about learning to support it.
Service and support. Obviously, it's a learning experience, learning how to design, learning how to orient, learning how to pick the right materials, the right speed in which the laser travels if you're using a laser system, or an ink system if you're using an ink system. That kind of learning, yes, is kind of up to the end user. But as far as the repair and diagnosis of the equipment, most of these manufacturers have the ability to dial into it and check certain aspects of it to find out where the fault might be. And they will ship a replacement part overnight if necessary. And as a last resort, have technicians that will come out in the field and do repairs.
Switching gears from the equipment, there's a question: if a piece is made from a 3D direct print, can it be melted and reworked in the studio?
Sure.
Okay. Yeah. So it doesn't change the metal composition at all. It's just a different way of building it up.
Mm-hmm.
All right.
You could use it as a building block. You could cast things and 3D print things and put them together and make something else.
Mm-hmm.
Or for that matter, fabricated metal. You want to add settings to a piece that you have printed. That would certainly be possible. If you wanted to use a platinum setting in a piece that you had printed in gold, you would use the traditional methods of soldering for that.
Okay. We have a question about the process of making the metal powder.
Mm.
It's a little bit of an esoteric industry. There's a couple of players that it's very widely done, I would say, in engineering metals, base metals, stainless steels, aluminums, etc. When you get to precious metals, there are precious few that do it and do it well.
In Italy. Italy's really like Legor Group and
yeah.
Gold, and that's where we're seeing a lot of precious metal powder.
Mm-hmm. Yeah, it is. It's not an easy process. It takes quite a bit of expertise. Effectively, how it's done is you take stock metal or liquid metal and you send it down a chute and various technologies, but it spins it off into particulate that cools and forms powder particles. And then there's a sieving process because you end up with very, very tiny micron pieces that are too small to use in the printers and some that are much too big. So then you have to, sieve and sort and get down to the range of particle size that works.
So this is what my company does, is we produce powders. And there are a number of ways of producing powders. The lower melting temperature materials, things below 2,000 degrees centigrade, are made generally by what we call gas atomization. And if you think of that like a perfume sprayer, only with heat, basically we are melting the metal either from a wire form or a crucible form, and then putting an inert gas behind it and spraying the metal. And as it falls, it cools and forms a spherical shape as it is melted. As you get into the higher melting temperature materials, things like titanium and platinum and tungsten, tantalum, niobium, these materials that are used more for aerospace applications and medical, they're usually made by plasma atomization or plasma spheritization, where we reach temperatures of 10,000 degrees Kelvin, like on the sun, and do a similar operation. They can't be gas atomized because generally the materials that you would melt them in would be destroyed by the time you got them up to temperature. So the higher melting temperature materials are done one way and the others are done another way. All of them are spherical. The concept of spherical powders is what you need, and generally there's a certain particle distribution size that is used for each individual technology.
So I love your perfume atomizer example. I think that's fantastic. Now, knowing that Susan Crowe asked that question and that she has a very particular interest in responsible design, is this a safe, responsible process, or are there dangers in it?
It's a green process. The atomization process, everything goes in, comes out. There's nothing that reaches the atmosphere. The same thing with plasma technologies. Everything is contained. And the additive manufacturing process is rather green as well. We don't have any investment that goes back into the ground. We don't have any real effluent from the process. Everything can be remelted and reused.
Well, and even the binders are fairly organic, aren't they?
They do present some problems in carbon uptake depending upon the alloy, but not so much for the jewelry industry. It's more about, the physical properties of a particular metal. But we don't see any real uptake of carbon for MIM processes in precious metals, so we wouldn't expect to see it in binder jet for 3D printing.
I do see one question about whether there's any difference in the ultimate metal color if you cast it versus print it. No,
Nope. Same stuff.
Same stuff. Wow, I've kept you guys late. I've still got some questions coming in. I guess while I wait to see if there's just a few last questions, is there any particular thing that each of you want to share with the audience that you think they should know? Or that you think I should have asked and I didn't?
No, I think you did a great job.
I'm just looking for strokes here.
In time, the costs for these things will come down. These machines have come down tremendously, and the technology is advancing every day. So jump in, take a few designs, send them to a bureau service of some kind, and try it. Yes, it'll be a little different to polish. It'll be a little different to play with. But what else have you got to do right now?
Veronica,
try something new.
I agree with Steve. Just send a file to a company and just try it out and see how it turns out for you. If you like, if you don't like, it's very interesting. It's a different way of approaching the jewelry process. Instead of casting, just send it out to print and try a different material. You probably will be, impressed as I was.
Show us your earring, Veronica, so people can see your work.
So this was one of them that was printed.
Oh, bravo.
Yes.
Very nice.
So I had to, like that, I had to change a lot of the angles in order to print for the metal straight. But it's very interesting. It really is absolutely an incredible experience. Just try something different.
So I'm going to material. You don't need to worry about the angles with binder jet printing.
Yes and no.
Well, not as much. Not as much.
Parting thoughts from you, Arjun?
No, I mean, I'm like the other panelists here. I think that the best way to get a lot of questions answered is to just try it out. And as Steve and Veronica mentioned, you could use bureaus to do that. I think experimenting with not just the printing of parts, but around design as well, and getting your hands dirty in CAD tools. Some of them may be more suitable for the jewelry industry than what we typically see from our customers. But I think, getting in on the design side, trying things out, trying different technologies too. I think hopefully one thing that's come to light over this time is that not all metal 3D printing is created equal. There's different technologies and different vendors, and there's nuances to each. So it's worth just dipping your toes in and getting a feel for what's out there.
Very cool. So we are totally out of time. We have kept Veronica up way past my bedtime. So I have no idea what time you normally go to sleep after 2 a.m. in China. I do see we have some additional questions. If you guys would reach out to our experts and ask them, that would be fantastic. Or send an email to me and I'll make sure we get an answer for you. I want to thank Arjun and Steve and Veronica for being our experts today. You've brought amazing information to our audience. And I want to thank MJSA again for producing this series. We so appreciate all the things you do for the jewelry industry and the education you provide. It is invaluable. And I want to thank our audience for joining us and for hanging out for a long time with us for questions and running long. So you guys are all amazing. Thank you so much.
Great.
And stay healthy.
Thanks, everyone. Thanks, Andrea.
All right. Take care, everybody. Thanks again. Bye.
Take care. Thank you.